In order to understand dark matter, we need to understand regular matter. We are carbon-based. That means we have carbon in us and oxygen, a little bit of hydrogen, a little bit of other elements. But when you look at the periodic table, most of the material in the periodic table is not very important in the universe. Most of the universe, 79% is hydrogen, another 20% is helium, and only 1% is all other elements in the universe. Now, let's look at what these helium and hydrogens are made of and all other elements are made of, which is called the regular matter, and that's in the second part on this slide. It's called the standard model of physics. Standard model of particle physics involve quarks. Everything, hydrogen, helium, etc., is made of up and down quarks. Up and down for proton, up, down, and down for neutron. And electrons float around. That's it. It's called the first generation of the standard model of particle physics. Then we have charm strange, top and bottom, particles called neutrino, mu neutrino, and tau neutrino, etc. And they're gauge particles. All of those particles that are not up and down are already not regular matter, are not the standard type of matter. But when we will be talking about dark matter, it's not even there. Most of the universe, 78% of all the matter in the universe is in form of dark matter that's not only not in the periodic table, but not even in our standard model of particle physics. It all started with Dr. Vera Rubin in the 1970s. She was looking at our companion, the nearby galaxy in Andromeda, and looking at how the stars were orbiting the center of the galaxy. The spiral arms of that galaxy were moving around the center in a weird way. You'd expect the spiral arms to spiral slower and slower as you go outwards, but you would be wrong. They actually don't go as slow as they should, which means that in the middle there's way more mass than you would expect just from looking at the light. The first picture is from a nearby galaxy, the second is the one that Vera Rubin actually was using, and the third is a picture of Vera Rubin herself. Vera Rubin was actually smart enough to look at a picture that was 40 years older, and in the 1930s there was a guy by the name of Fritz Zwicky that claimed that the amount of matter in clusters of galaxies doesn't look right. There must be some unknown matter, which he called dark matter. For 40 years nobody looked at his suggestions. Then in the 1970s, again several people looked at those clusters of galaxies and looked at the speeds of those galaxies, which were influenced by something unseen, and a new kink was to look at the galaxy beyond that, and those arcs that you've seen in this picture are actually lensed images of galaxies that are way further than the regular galaxies that you're seeing in front of you. And therefore this is acting as if it was a gravitational lens. And that gravitational lens tells us that in the cluster of galaxies there's lots of material that's not in the form of visible galaxies at all. It would take a long time until we saw that this is non-baryonic matter, which means matter not made of up and down quarks. Here's a recent picture of multiple clusters in a large portion of the sky, and the map, dark red being the denser, dark blue being the least dense, of that region in terms of dark matter. As you can see, what we are observing is that visible galaxies are more or less in the vicinity of dark matter, but there is no obvious one-to-one correlation. There is no dark matter on a galaxy, but rather within the potential well of the dark matter is where those galaxies form, and not vice versa. Whereas the previous picture was more or less two-dimensional, this one is three-dimensional with depth added in. So those clumps that you're seeing in front of you are clumps of dark matter, and as you're looking towards the right and far off, that's further and further from Earth, where those clumps are located, at the same exact region that the previous picture was taken. Here is the more recent picture. In it you see a collision of two clusters. Each cluster is made of tens, almost hundreds of galaxies, depending if you're looking at mini galaxies as well. So hundreds of galaxies collide with another cluster of hundreds of galaxies, but it's not just the galaxies that are colliding, but also the dark matter potential wells associated with them that are colliding. What seems to be happening is that the light producing material kind of slows down, whereas the dark matter that's weakly interacting continues further. That's the equal height maps with the green lines that kind of went through, whereas the matter that makes visible galaxies is still left behind. That's kind of cool. It tells us something about what this dark matter is made of, namely something that's very weakly interacting in any way except for gravity. This dark matter stuff goes by the name of WIMPs. Okay, not because those particles are really wimpy, but it's an acronym for weakly interacting massive particles. Yeah, I know, not much imagination there, but I still kinda like the name. Maybe because I'm a nerd. That's not an acronym for anything, just a description. In any case, this huge picture that you're seeing in front of you is a machine very deep inside the Alps. They turn the light off and connect the voltage and look for particles that are called WIMP decay. Basically, those huge, massive, weakly interacting particles, if they meet their counterpart, they explode with very high energy, and we may detect that. Calculations show that we should see a few tens of them per year. So far, there are a few candidates, but the jury is still out on those. In this picture, you see an experiment called Ice Cube, another way of looking for dark matter particles. In this particular case, we're looking for weakly interacting massive particles meeting their counterparts, exploding in the process, and giving off neutrino. That's the same neutrino that we described when we described what's going on in the center of the sun and coming towards Earth. Only these neutrinos that we're looking for in Ice Cube are high energy neutrino, way higher energy than the ones coming from the sun. They will be the result of those WIMPs exploding while meeting another WIMP. So when WIMP and WIMP meet, there's kind of an explosion that's barely observable, and it's called Ice Cube because the experiment is literally in an ice cube. It's in Antarctica, going deep to about 2.4 kilometers, so that's over a mile deep, and at that depth there is no light, there is no cosmic rays, there's nothing to disturb you except for things that can weakly interact and therefore go into the Earth or into 1 mile deep and leave their mark. Again, this is a very new development, and we don't have any clear-cut observations as of yet of this dark matter. And yet, from those observations of galactic motion that Vera Rubin was looking at in the 1970s, or cluster motion watched by Zwicky and then in the 70s by all sorts of people, including Vahy Petrosyan from Stanford, we look and see that dark matter is a huge portion of the universe. 63% of matter. I said a larger number because I did not include photons and neutrinos in the calculation, only the atoms. As you can see, 12 versus 63%. You can kind of restructure that as you please. One of the best ways by which we can tell that there is dark matter is by looking at the amount of helium produced during the Big Bang and modeling how the universe has expanded since. Again, that gives support to a large part of the matter in the universe being in the form of dark matter, namely non-neutrons, non-protons, non-up and down quarks. In this lecture, I'm not going to explain the whole issue of dark energy. Rather, I'll emphasize the difference between dark energy and dark matter. Dark energy is not dark matter. Rather, dark energy supposedly is 68% of the total energy in the universe and responsible supposedly for the acceleration of the universe. In the Big Bang picture, if you go back in time, when galaxies were way closer together and then they expanded, you would expect gravity to slow the process down. But we're seeing the other way around, the process actually increases. Most scientists, but we're just talking here simple majority, not a scientific support, think that this is because of this dark energy that drives the universe along. That one is way more controversial than dark matter is, only we are seeing some evidence of it in independent experiments, and we will talk about that in the future. This weird symbol above the numbers in the two columns that you're seeing is called omega. Omega subscript m is omega matter, which means mostly dark matter. Omega sub v is the dark energy. And as you can see, if you're going from the numbers at the very bottom all the way to the top, the 5 and 0 means that we have lots of dark matter but no dark energy, and the universe closes upon itself, meaning it expands then contracts. 1 and 0 is our thinking until the 1990s, mid-1990s, dark matter just about right for having a universe in between open and closed. And then, since then, we've seen the 0.3 and 0.7, which is the universe that's actually accelerating its expansion. Hence, it's known as the accelerating universe. There is no doubt about that. But why it is accelerating is probably due to that dark energy. If it is, then dark energy is an appropriate matter, but it could be that this acceleration is due to some other competing theories. This picture is a picture that kinda looks at the evidence for the dark matter versus the dark energy that we have. Several sources here show that we probably have some dark energy, only this is experiment dependent, hence we will talk about it in future lectures. Live long and prosper.